Hey guys, welcome to 8.1. This is our very first video of the second semester, and it's going to kick off our first unit of the semester over chemical quantities. So this particular video is over the term the mole, which you guys have already heard because we've kind of introed that yesterday. The mole is really just a word that's used to stand for a number. The mole is not a unit. I repeat, the mole is not a unit, is really just a number. And so what we've learned so far is we've learned the mole stands for a particular number of things, of particles. And we learned again yesterday that the mole stands for the number 6.02 times 10 to the 23rd power. 6.82 times 10 to the 23rd power. You're going to see, over the course of this video, you're going to see quotes or blocks that kind of pop on the screen. Anything that pops up on the screen inside of one of these boxes should be included in your notes. And so what the question that you should be asking yourself now is, why do we use it? Like, why do we need the mole in chemistry? What is it used for? Well, to help you kind of visualize the need for the number, the mole, I drew a sample chemical equation here on my paper, and as you can see, I've shown two different types of atoms. There's element A and then there's element B, and I've shown that there's two atoms of element A that will combine with one atom of element B to make your product, okay, which is just like one molecule of ABA, which is essentially like A2B, right? So we have two atoms of A, one atom of B, and it forms like this compound. That's essentially what our chemical equations look like. We look at how many atoms are needed to form a product, right? But this isn't practical. Even though this is how we've always seen our reactions, this is not practical because in the lab, we never just want to make one molecule of A2B. We want to make lots, millions and millions and millions of this product, right? We don't want just one molecule. What are we going to do with that? And it's really impossible for us to measure, especially in our high school chemistry labs. So we have to measure something much bigger, much greater. Think about it in the way that, like, if this was, well, chemical reactions are very similar to cooking, okay? Essentially, cooking is a form of chemistry. When you're cooking a cake or baking a cake, you have to use certain amounts of your ingredients to make your product, which is the cake, right? Well, what if our recipe looked like this? It looked like we had two atoms of flour, although flour is not really an atom, it's a compound. So let's say you have two molecules of flour, one molecule of sugar, and you'll make one molecule of cake, which I know there's a lot more that goes into making a cake, but let's just simplify and pretend that our recipe said you need two molecules of flour, one molecule of sugar, and you'll make one molecule of cake. Well, that sucks. I mean, who really wants to eat one molecule of cake, right? I mean, I want like a whole cake, and that's way more than one molecule. So instead, our recipes don't look like two molecules of flour. They say what? They say 2 cups of flour and 1 cup of sugar will make one cake. And so what is the cup? Why do we use the word cup? Well, we need to find a number, okay? And so the cup kind of stands as a number. And it tells us how much of each ingredient we need. And the cup is a much more useful term for us than molecule because we know how to measure a cup of flour, right? Versus we're not going to be able to measure one molecule of flour. So in chemistry, we have the same problem. How do I get 2 atoms of A and 1 atom of B? I can't just pluck those out of a bottle. So we use something called the mole. The mole is a much larger number, so it can stand for a large amount of ingredients. Essentially, a reaction is not helpful if it only produces one molecule. It would be much more helpful if it produced millions and millions of molecules. If you want a lot of your product, then you're going to need a lot of your reactant. And so our number that's going to stand for a lot of our reactant is going to be the mole. When we say that we need like 1 mole of atom A, or we need 1 mole of element A, or 1 mole of element B, what does that really mean? Well, if you think about the term dozen, A dozen stands for a number, right? It doesn't stand for a unit, it just stands for a number. A dozen eggs stands for 12 eggs. The word dozen is a direct replacement of the number 12, okay? Our unit comes after the term dozen, okay? So this is our unit. Here we have a dozen books. Dozen is not the unit, books is the unit. So the dozen stands for the number 12. So we have 12, and again, here's our unit, books. This is very important. We call it Avogadro's number. Avogadro is the one who invented, so to speak, this number. And so I have a couple example problems here that I want to work with you to kind of make sure we understand the concept of the mole. So if I have 1 mole of aluminum foil, aluminum foil is only made up of the element aluminum. Okay, so how many aluminum atoms would I have if I had a mole of aluminum? Well, 1 mole stands for the number 6.02 times 10 to the 23rd. So if I had 1 mole of aluminum, I essentially have 6.02 times 10 to the 23rd atoms of aluminum. What about the next problem? If you have 6.02 times 10 to the 23rd skin cells in your body, how many moles of skin cells do you have? We know this number stands for 1 mole, so that means we have 1 mole of skin cells. If I had 5 moles of sugar, how many molecules of sugar do I have? Well, that one's a little bit tricky. We have 5 moles of sugar, right? 5 moles. We know that 1 mole equals this number, right? 6.02, Avogadro's number. So all I have to do is multiply 5 moles times Avogadro's number, and then I'll get how many molecules of sugar. Okay, I don't have a calculator on me, but that's essentially what you would do to find how many molecules of sugar. How do we know how much 1 mole is? Obviously we know how many atoms, but I just told you that it's impossible for us to count atoms, right? We're not going to sit down and count 6.02 times 10 to the 23rd atoms so that we can have a mole so we can react it with other things. So since we can't count the mole, how are we going to know how much 1 mole is? Well, scientists that are infinitely smarter than I am have discovered how much 1 mole of each element on the periodic table weighs. The molar mass of an element is the mass of 1 mole of a substance. So 1 mole of a substance, and however much it weighed, that would be its molar mass. On our periodic table, we have the molar masses of every single element. The molar mass is going to be the same number as the atomic mass, as the average atomic mass of an element. For example, if you had 1 mole of hydrogen, it would weigh this many grams, 1.00794. If I had 1 mole of lithium, it would weigh 6.941 grams. If I had 1 mole of sodium, it would weigh 22.98 blah, 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 blah grams. Usually, we only go to the hundredths place when we're looking at molar mass. I think all of your periodic tables only go to the second digit after the decimal. One clarification I want to make is the difference between atomic mass and molar mass. So atomic mass is always given to you in AMUs. That's atomic mass unit. So the atomic mass unit, or the atomic mass of hydrogen is 1.00 AMUs. The molar mass of hydrogen is the same number, but it's a different unit. Molar mass is always measured in grams, okay? Because we're talking about a mole of hydrogen atoms. So it's the same number, but instead of weighing 1 atomic mass unit, it weighs 1 gram. So atomic mass is always in AMUs and molar mass is always in grams. It's the same number, and you can find this number on the periodic table. Okay, so let's do some guided practice here. If I asked you to find the molar mass of magnesium, I would just look on your periodic table right here, and I would look at this number, and the molar mass of magnesium would weigh 24.3050 grams. I would just add my G on. So that's the answer to the first example question. The second example question is asking about an element called germanium. Here's germanium over here on the right side, and germanium's average atomic mass is 69.723 AMUs. Its molar mass is the same number, but just grams on the end. Finding the molar masses of elements is as easy as just going to the periodic table and finding the number underneath the element symbol. The last thing we're going to learn is how to find the molar mass of a compound or a molecule, which is a little bit more difficult. If I gave you a compound or a molecule like H2O and I wanted to know its molar mass. Well, H2O is not on the periodic table with a number underneath it, but hydrogen is on the periodic table and so is oxygen. So I'm just going to do them separately and then add them together. Let's do hydrogen first. Here I have 2 hydrogens. The molar mass of hydrogen on the periodic table is 1.01 grams. Since I have 2 hydrogens, I have to find the mass of 2 hydrogens. Okay, so H2 equals 2 times 1.01, which turns out to be 2.02 grams. Okay, so that's the molar mass of 2 hydrogens. In the formula, I just have 1 oxygen. Okay, so I don't even really need to put a number 1 here and put the molar mass in parentheses because it's just 1. So I don't have to put that at all. All I have to do is write the molar mass of oxygen. So I look on the periodic table. The molar mass of oxygen is 15.999. Okay, so 15.99 grams is just 15.99 grams because I only have 1 oxygen. And then I'm just going to add these 2 together. Okay, the molar mass of hydrogen is of 2 hydrogens is 2.02. The molar mass of 1 oxygen is 15.99, and so I add them together and I get 18.01 grams. That's how much mass 1 mole of water is. Now, one thing I did not clarify to you guys is the unit for molar mass. Molar mass isn't just grams, it's actually grams per mole because it's how many grams are in 1 mole. So for each of these units, I actually have to write grams / MOL, okay, because it's grams per 1 mole. Here are some example problems. I'm not going to do all of them with you. I'll do maybe 2 with you and then go over the other 2 in class. For these ones, I've not given you the formula. I've given you the name. So your first step is to write out the formula given the name, which is something we learned last semester. Then you find the molar mass of each atom like I did. You add them together and then you use that unit. So dihydride, it's a covalent compound, right? Because I see these prefixes. So dihydride is really just H2, okay? And so H2, I know since there's 2 hydrogens, I'm going to put 2 on the outside. And then I find the molar mass of hydrogen, which is 1.01 grams per mole. And then when I multiply that together, it's just 2.02 grams per mole. And that's it because dihydride is only just H. It's only 2 H's. What about sodium chloride? Well, sodium symbol is Na, and chlorine is Cl. Since there's no prefixes, I know it's ionic. Why is that important? Well, ionic compounds, in order to know the formula, I have to make sure that each ion balances each other out. So sodium, it's in group 1, so its charge is +1. Chlorine is in group 17, so its charge is -1. So you'll still need to memorize the charges. These charges automatically even themselves out, so I know my formula is NaCl. So all I have to do is add these together to get my molar mass. Now, why did I not multiply by anything? Well, because I only had 1 Na and I only had 1 Cl, so I don't need to multiply these numbers by anything. So the molar mass of sodium chloride, when I add them together, is 58.42 grams per mole. Remember, I'm always going to the hundredths place on my molar masses. And I'm going to let you guys try and work out iron 3 hydroxide and ammonium sulfide on your own, and then we'll go over them in class. Ammonium is a polyatomic, so you need to look on your polyatomic chart for that one. And then iron 3, remember the Roman numeral stands for the charge of iron. So this iron is a +3 charge. And that is it for this video, 8.1. Y'all have a wonderful day, and I'll catch you later on 8.2.